right? I thought there'd be data. Is anyone out there?
Okay, welcome back. Happy Friday. Congratulations on making it to your first day off, the Labor Day Monday. I assume you can hear me or someone would have been waving by now. Yeah. Today I went back into, I posted module 6 for today, but I went back into module 5 just to, because I thought it went there, just to post a fun table that you don't need to look at. Last time we defined the beta distribution, and we got it from looking at two IID gamma random variables, x1 and x2, and computing the distribution for x1 over x1 plus x2. And we saw a relationship, and we've also talked about other relationships between the exponential and the gamma distribution. So just wanted to quickly show you this table. This is my all-time favorite table. I have it on a t-shirt. It was originally written down by a guy named Lemus, and this appeared in someone else's book. So in the title on the bottom, it says adapted from Lemus. And I just think it's cool. They're all related. And you don't need this for this course. It's just kind of interesting. But if you are trying to use it, note that I didn't write it. So it appears, for example, to me that they're using 1 over beta in place of the beta of the gamma distribution. So some of these things, you know, might need a little bit of tweaking. But how cool is that? That's cool. I like it. So I don't know if you could see my mouse, but here's the beta, here's the gamma, and there's the transformation we made. And from the gamma, you can get the exponential by taking one of the parameters equal to 1. And there's a whole lot more for us to learn. So we've talked about the geometric up in the upper left. Again, I don't know if you could see my mouse, so way upper left. And then it has a relationship with the negative binomial just to its right. And yeah, so that's just for fun. You don't need that table for anything in this class. At the end last time, I just have one thing to finish up on that problem before we move on to the next section. And that was we did a transformation with gamma random variables, and we got what I called a beta random variable or beta distribution. And I wanted to define for you the beta function. So if we have x, a random variable with the beta distribution with parameters a and b, those are non-negative parameters, and that means that the PDF is 1 over this thing called the beta function. So it's kind of a big kind of weird b or whatever, but it's usually typed up kind of more like a calligraphy b. And then x to the a minus 1, 1 minus x to the b minus 1, oops, on the interval from 0 to 1. And I was telling you last time about how this is one of my favorite distributions because it's so flexible in modeling things between 0 and 1. But what I didn't have time to tell you was what this thing is right here. This is known as the beta function. And so for any a and b greater than 0, the beta function is defined. So those dots are defined as the integral from 0 to 1 of x to the a minus 1, 1 minus x to the b minus 1. Wow. I'm telling you right now, think of your favorite integrable non-negative function, then declare your name, the name of the integral of that function, and then you've got your own distribution. I mean, this is the constant that it needs to be. This is not really groundbreaking. We saw this also with the gamma distribution. And one relationship that is a cool relationship, if you want to see the proof, I think it's on page 75 of the notes. I don't want to take the time to do it today. It's not bad, but we have to think about double integrals and transformations with Jacobians. And that is that the beta function of a and b can be related to the gamma function in this way. It's gamma of a times gamma of b over gamma of a plus b. And if you remember the previous problem we worked on, we started with 2 gammas and got something sort of beta. And so we had gammas in our joint PDF at the end. and those could have been manipulated to turn into this exact beta function constant. Not too important that you know that, unless you want to simplify things as much as you can. Just know it's just another constant. Okay. We are in section 1.4, chapter 1, section 4, and this is about mins and maxes. And I'll tell you what that means. And I guess before talking about mins and maxes, I wanted to talk about briefly about sampling distributions. Okay, so suppose that I have an exponential distribution. If we were in the classroom, I'd usually say out in the hallway, but I don't know, in here, and you can't see it. I have something that's going to generate exponential rate lambda random variables. And although this class isn't about simulation, I will tell you how to do this particular thing within the next week or two. So what does that mean? It means get a list of numbers and then start making a histogram out of that list. So the exponential rate lambda distribution starts at lambda at x equals 0 and then goes down, you know, exponentially. That's not supposed to have that bump. It's just nice swoop exponential. I can't even stand to see that. It's going to be worse this time. That's a little better. So, you know, the area under this curve is probability. So we expect to see a number, say, between 0 and whatever this is. I have no scale on here. Let's say 2, with probability equal to this area. And if you were to start somehow generating numbers from this distribution and building up a histogram of what you see, assuming that it is scaled properly so that you have like a relative frequency on the y-axis, if you superimposed the exponential distribution, it's going to fall, like it should fall right on that. So if you're ever simulating random variables according to a known PDF, you know, a good visual check would be to make a histogram and then superimpose the PDF. Because assuming you've scaled things right, making a histogram makes the area of these rectangles the probability that you are between these points in these bins. So this is not a simulation course, and I don't even think we're going to make another histogram, but I just wanted to give you a sense of what it means to see or sample random variables coming out of a distribution. So let's look at this picture again. Suppose I am sampling from the exponential distribution. That is just going to be producing a number and producing another number, producing another number and another and another and another. And there are going to be way more of them piled up down by 0 because that's where all the area is under the curve. Does that make sense? So let's say I took a sample of size n. So I'm going to let x1, x2 out through xn be a random sample of size n from the exponential distribution with rate lambda. I don't know why I'm writing that part out. We have notation for this. So exp rate lambda distribution. So that means I have n little x's on my x-axis over here. And if you look at the minimum of those values, that appears right here. It's a little hard to differentiate, but I have a minimum in this sample. And if I were to throw out the sample and then get a new random sample, so I'm going to just kind of draw it on a higher line here. Or maybe I'll give it its own graph. So a new random sample of size n, I don't know what n is, but would produce some values. And the minimum in this case is now here. the minimum of these samples, these random samples, is another random variable. And it has what is called a sampling distribution. It's the same thing if you've ever talked about a distribution of X bar, a sample mean. If not, that's fine, we'll talk about it. And things like the central limit theorem, don't worry, we'll talk about it. But if you've heard of those things, you know, you can imagine trying to generate a random sample and not actually getting it yet, because once you have numbers, the randomness is gone. So we want to give prescriptions for confidence intervals and hypothesis tests and things like that for someone who is about to grab a random sample. If you compute the minimum of a sample of size n, it's going to fall somewhere, and the next sample you take is going to fall somewhere else, and the next sample you take is going to fall somewhere else. And probably it's going to be really kind of piled up towards zero. It's going to be hard. Again, I don't have a scale here, but it's going to be really hard to get like a minimum up here. And it's going to have its own PDF. And that's what we're out to find right now. So let's go for the PDF of the minimum of the exponential distribution. And just before I do that, I want to give you notation. So if we have x1, x2, out through xn, a random sample, remember, I've already defined the words random sample. It means that they're IID, so they're independent and identically distributed. Then there's two common notations for the minimum in the sample. So one, which is the one I think we're going to use, is x1 in parentheses is the minimum of x1 through xn, and x2 in parentheses is the next smallest out through xn in parentheses, which is denoting the maximum of x1 through xn. So some people denote these, and I do too. I kind of like it because it shows you the dependence on n. But another notation for the minimum is x1 colon n. I really like that, but I don't like it so much when I'm writing notes on a board, which I guess I'm not, but I don't know. It's easier to write the others fast, I think. And this one is sometimes denoted by x2 colon n, and this one. So I really like this because it shows you what the sample was taken out of, because technically, if you see an x sub n, it could be the nth order statistic, which is what it's called. These are called order statistics. It could be the nth one out of 2n of them, but we're not really going to have anything like that come up. So if you see x sub n in parentheses, it is the maximum value of a random sample of size n. Okay, so let's find the distribution of the minimum for the exponential distribution. I could give you a formula in a box, or we could just do it. And let's just do it. So I have x1 through xn, IID, exponential with rate lambda, and let's find the distribution of the minimum, which we've just decided to call x sub 1 in parentheses. Okay, so remember the PDF for the exponential is f of x equals lambda e to the minus lambda x on 0 to infinity. And the CDF, the cumulative distribution function for the exponential, not the minimum, but the original distribution, we use a capital F. It is the integral from 0 to infinity, lambda e to the minus lambda x. Well, I'm going up to x. So let me say lambda e to the minus lambda u du. And this is 1 minus e to the minus lambda x. And this holds for x greater than 0. And I'm kind of not really into indicators with CDFs, which might surprise you because I'm so into indicators. And the reason I'm not is because they're not always n0 otherwise. As a quick example that you might not even want to write down for fear of ruining your notes, if we had a uniform distribution on the interval from 0 to 1, that means we have a flat line at a height of 1 so that the total area under this is 1. And the CDF, so this is, let's say U, all right, I guess I'm really writing this. U uniform 0, 1. The PDF, let me call it X and not U. The PDF is just the indicator from 0 to 1 of X. And the CDF, this is not going to fit in the corner. So the CDF, I want the total area up to any particular X in here. And that total area is given by this area, which is X times 1. So the CDF is just X, as long as little x is between 0 and 1. And so this is the probability that the uniform is less than or equal to X. And the uniform in this case will not be less than or equal to -2 because it's definitely between 0 and 1. So you're going to get 0 if X is less than 0. And the thing is that when you get above 1, it's not just 0 everywhere else. It's actually 1 for X above 1. And this is why I don't tend to use indicators for CDFs, because you've got the main, part that defines the CDF. And then it's not always and 0 otherwise. This one is 0 sometimes and 1 sometimes. And we absolutely can write this with an indicator, but it makes things even more complicated because it would have to be a sum of indicators and a weird thing. So I know that seems very hypocritical of me because I'm all about the indicators, but I really don't like using them for CDFs. Okay, so that was a big aside. But this CDF is defined for X greater than 0. And in fact, it is 0 for X less than 0. And for theoretical reasons, which we'll talk about later, I could talk about it now, but I kind of don't want to. Too many other things to talk about. CDFs are always right continuous. The CDF for like a constant random variable, suppose you take on the values 0, 1, and 2 with some probabilities. The CDF would look like it would be flat, and then at 0, it would jump up by whatever the probability of 0 is for your distribution, and then it would stay flat, and then it would jump up by whatever the probability of seeing 1 is, and then it would jump up, and it would end at 1, a height of 1. And by forcing these to be right continuous, I'm going to have open circles, not there, open circles from the left and closed circles to the right. And although there's a more technical measure theoretic reason for having them be right continuous, the easiest thing to say at this time is it just doesn't make sense to not be right continuous, because you are trying to accumulate area under a curve, or in this case, add up a bunch of individual probabilities. And so you have no probability, no probability, no probability. And then when you hit 0, you jump up to here to some, 1/3 or whatever number that is. And it's that is telling you that the probability that this X is 0 is this height H. But if I put the dots the other way, if I make this left continuous, then, this picture has an interpretation. I've got probability on 0. That's where it jumped. And if you do it the other way, it's really hard to interpret. I'm going to jump up immediately after 0. I suppose we could talk about things like that, but it certainly wouldn't describe discrete distributions where we want to look at specific values. So that was just enough of a diversion, and not enough. That was just enough to be annoying and not enough for you to totally get that stuff. But I am digressing. We will come back. Okay, what about the problem? Let's do it. Whenever you're finding the distributions of minimums or maximums, I would always suggest looking at CDFs, cumulative distribution functions. So we want to find the distribution of the minimum, and this is going to mean look at the CDF, the cumulative distribution function. I'm going to write this out for the minimum. So f sub the random variable x sub 1 in parentheses of x. You can put an x1 in there, but there's no need to. And you can put an x1 in parentheses in there, but there's really no need for that. That's just extra messy looking. It's just an argument. So this is the probability that the minimum is less than or equal to x. I'm going to just write this out just a few times just while you're getting used to this notation. So I've done nothing between this line and the line before, just written minimum differently. Okay, so imagine, if you will, a number line over here, and this little x is some fixed value, and we want the random sample. By the way, we only know things about the individual x's, so my goal now is going to be to rewrite this probability in terms of the individual x's, because I know they're CDF and I know they're PDF. And so if you imagine like a sample falling on this line such that the minimum is less than x, there is a lot of ways for that to happen. There's the sample I just drew. I could have them all less than x. I could have one less than x and then all the others up here. You know, I can't really tell you where the x's are by saying the minimum is less than or equal to x, which is why we want to turn this around and write this as 1 minus the probability that the minimum is greater than x. I should say that we will only be talking about mins and maxes for continuous distributions. If you have discrete distributions, then you have the problem of possibly having multiple observations of a minimum value, which is fine and you can handle it, but it sort of will be an ad hoc kind of, you have to handle it when it comes up kind of thing. We don't have a nice formula for that. Okay, so if the minimum of my sample is above x, that's going to happen if and only if everything in the sample is above x. And that's going to make this guy equivalent to 1 minus the probability that x1 is above x, comma, and x2 is above x, comma, and xn is above x. And because they're independent, and in the future I will do both of these steps at once, but I'll break it down for our first time. Because they're independent, remember the commas are like and or intersection, and because they're independent, you get to turn this into a product of individual probabilities. And because they're identically distributed, these are all the same. They're different random variables, but they all have the same x plugged in. So if you were going to compute this probability for any one of them, you would integrate from x to infinity the exponential PDF. It would be the same for every one of them. So by identicalness, I like that word, this is 1 minus one of these probabilities to the nth power. So I wrote above that this is, well, I'll just write it in here. This is inside the bracket 1 minus the CDF for the original distribution to the nth power. And if you go back and look at the original CDF, it's a 1 minus E thing. And so you've got a 1 minus, a 1 minus, a 1 minus. Be careful, you've got a lot of cancellation. But this is going to turn out to be 1 minus E to the minus lambda x raised to the nth power. And of course, when you take something to a power and to another power, you get to multiply the exponents. This is probably a recognizable CDF because we just wrote it down. But in general, at this point, you would say, okay, I know the CDF for the minimum. Let me take the derivative, get the PDF, and try to identify the distribution. So we have now the CDF for the minimum is 1 minus E to the minus n lambda x. So the PDF is the derivative. And you see another exponential distribution. This is n lambda e to the minus n lambda x. And I didn't drag the indicators through, but you're not really finished until you give the domain or support for this function. I won't really care if you do it, but I'm a little bit of a, it annoys me to suddenly slap the indicator on the end because then it's not equal to the line before. But the support, does everyone know what a support is? So I keep saying or domain. A domain is where the function is defined, but the support is where it is non-zero. So where it is quote unquote interesting. it's always the same as the original values. You know, the original x's are somewhere between 0 and infinity. And although you're not likely to get the minimum of a sample of size n be really large, there's actually nothing in theory cutting it off. So the support is still 0 to infinity. And so we have a nice known named distribution. This doesn't always happen, that you get the same type of distribution or even any known name distribution, but we've seen that the minimum is exponential with rate n times lambda. And what does that look like? The exponential distribution with rate lambda starts at lambda and then goes down all exponentially. And n times lambda, assuming n is greater than 1, is going to be larger. So it's going to start up higher. And since, you know, it's not going to go like this because the total area is 1, it's got to come down faster. So it's going to shoot down really, really fast. And that's going to put more probability or more area down towards 0, which is what we expect out of the minimum of the sample. Remember the x's I drew before, the minimum is always down towards 0. I say just do it, but if you want a formula in a box, basically what we showed is that for any continuous x1, x2 through xn, IID from a distribution with some PDF little f and some CDF capital F. You know, I didn't use the exponential till the very, very end of this. So we can go through the same sequence of steps. The CDF for the minimum, I scroll, is always going to be this guy. So that is 1 minus 1 minus the original CDF to the nth power. And so the PDF, you take the derivative and you get whatever you get. You get a formula in a box if you really want one. I'm going to get n1 minus the CDF to the n minus 1 times the PDF, because the PDF is the derivative of the CDF. So yeah, there were a couple of negatives that I went ahead and canceled. And then this is on the same support as the original distribution. So yeah, there is a formula in a box. Not really a box. A formula in a blob.
Question.
Yeah.
So where in this does where in the derivation does it go wrong if you don't have a continuous distribution?
It's really hard to deal with the continuous one because if you have if you're sampling from, say, a geometric distribution, maybe let's say the one that starts from 0, then it's, let's see. It's possible to get, so let's say in this list, let's say it's a list of 5, you get 3, 1, 2, 0, 2, let me do another one. The minimum appears more than once. And so the probability that the minimum is equal to some x, if you go and look specifically at the probability that x, the minimum, is equal to 0, this is going to be the probability. It's going to be a big sort of sum of things. It's going to be the probability you saw exactly 1 0 in there, or maybe 2 zeros in there, or also 3 zeros. You have to add all those up. And the minimum is not so hard, but it's definitely hard to talk about the kth largest. The problem really comes in when you're looking at the intermediate order statistics. So if you want like the 3rd largest, then like if you're going for, maybe you have n equals 5 and you're going for the PDF for x3, it could be that you would say, okay, I need to have So this is like if it was discrete. This is the probability that the third one equals this value x. And let me put in an actual value. I don't know, 2. It might be that you have like only 2 values appearing in your 5, and you don't even have a third largest. And when we try to write out a formula for the third largest, it's going to assume that there are 2 below it and the remaining 2 above it. No, yeah. A lot of it does work. It just gets messy because you have to consider what happens when you have multiple third largest things. Okay, guess what's next? The maximum. So for the maximum, I wanted to use this opportunity to talk about another distribution, which I guess you saw in homework 1, but we never really talked about, and that is the Pareto distribution. So here is a max example. I'm going to let x1 through xn be IID from the Pareto distribution with parameter gamma. There is something known as a discrete Pareto distribution, but no one ever uses that or means that unless they say discrete specifically. Okay, so the PDF, if you look up on the table, is f of x. By the way, this gamma is a parameter greater than 0. So this is f of x equals gamma over 1 plus x to the gamma plus 1 on the interval from 0 to infinity. Some people write it as well as they'll do gamma over x to the gamma plus 1 on the interval from 1 to infinity. You might see it written that way at some point in your life. So this is a Pareto distribution, and because this is a nice, like just power, this is gamma 1 plus x to the minus gamma minus 1, we can easily integrate it from 0 to x, and we can find the CDF. Capital F is 1 minus 1 over 1 plus x to the gamma. Yeah. And this is going to hold for x greater than 0 or equal. So new distribution. And let's look at the distribution of the maximum of that random sample. Okay. I might regret this. This is not, okay, we can do it, but I don't think it's going to have a name. The minimum would. So for mins and maxes, go for the CDF. The CDF for the maximum is the probability that the maximum is less than or equal to x. Because it's our first time seeing it, I'll write out the maximum of x1 through xn. And now if you think of the number line situation again, and x as a fixed number here, the maximum value in a sample, so dropping sample values here, the maximum value is less than or equal to x, if and only if all the values are less than or equal to x. That's the only way to get the maximum below x. So we don't have to do a 1 minus here to relate this to the x's. This is the probability that x1 is less than or equal to x, and x2 is less than or equal to x, and xn is less than or equal to x. And because they're IID, you get to break this product up into a product, and you get one of them to the nth power. So this is the CDF for one of them raised to the nth power. And I suppose we can forget about the Pareto PDF, although we don't have to, in order to get the general form for the PDF of a maximum, which Sam, is it Sam or Samuel?
Me?
Yeah.
Sam.
Sam. That part is definitely going to change from discrete and continuous because the derivative doesn't make sense, but I know that's not what you were asking. So the PDF of the maximum is n times the CDF raised to the n minus 1 times the derivative of the inside, which is the PDF. So I shouldn't have picked the Pareto distribution. We can definitely finish this problem, but we will not be able to name the distribution. And that doesn't mean it's not a valid thing to work with. You know, we might find ourselves needing this distribution at some point. But at this point in the class, I wanted everything to be so neat and tidy and everything to have names. But I'll just finish it off for the record. The PDF for the maximum is going to be n 1 minus 1 over 1 plus x to the gamma to the n minus 1 gamma over 1 plus x to the gamma plus 1. And this is going to live on 0 to infinity because it lives on the same support as the original. So there's no name here. But if anyone, you know, approached you on the street and asked you for the expected value of the maximum of the Pareto, I would find this, and then I would put an x in front of it and integrate. You know, you can find the expected value of the maximum by first finding its PDF. Of course, if it has a name, then you can look in your table. So yeah, I guess I should put this in a blob, the formula or the PDF of a max. Now, something I was already planning to give out to you in the form of typed up notes outside of the course notes is PDFs for like the kth order statistic or joint PDFs for, actually I am going to have you on the next homework derive the joint PDF for the minimum and the maximum. The reason I'm just gonna hand it out for optional reading if you care, because for the purpose of estimation and what's coming ahead, I don't think we're going to ever need any of the other order statistics, but I think you might feel more complete if you see them. So I didn't want to take the time to do them in lecture. Where might we want one? Imagine that you have x1 through xn, IID uniform on 0 to theta. That means they're going to fall between 0 and theta, which, by the way, theta is an unknown parameter, and they're going to have a nice flat line distribution. And the height would have to be 1 over theta, so that the total area is 1. And later on, we're going to talk about estimating these unknown parameters based on the random sample. And so if you did not see this PDF, but instead just saw values coming out of the sample and you didn't know theta, your best guess is probably that theta is right here at the max that you saw, or maybe plus a little bit more because you think the probability I'm going to get all the way up there is probably small if n is small. So a big part of this course is going to be estimating unknown parameters for distributions based on random samples. And we're going to name maximums and minimums for distributions that have their parameter kind of in their support. We're not going to find ourselves needing, again, the other ones, but I want us to find I'm going to put this on the next homework in a walkthrough, like do this, then you've done this. See, because we might be interested in the PDF of the range of the data, so the max minus the min. And that's a function of the max and the min, so we would need that joint PDF. Okay. We are done with section 1.4. Yay us. So I'm just going to I only have the time to start a little bit into 1.5, which is a pretty powerful section, and it's about moment generating functions. Which are affectionately referred to as MGFs. Oh my God, you guys, I just spent $180 on a little cup of 5 bugs. 5 bugs. They're being shipped to me right now from Nevada. Little bugs.
These are food for a pet?
No, I started yeah, I can't do this anyway. I have a lot of reptiles and I have them in bioactive enclosures. So I have isopods cleaning and they keep the substrate clean and they eat waste and stuff. And I've since started getting into the more rare isopods. I saw one for $1,000. It's a little bug. So I think well, I don't know. I think depending on which clock I look at, let me just give you a definition of a moment generating function. So for a random variable x, and this can be discrete or continuous, the moment generating function, when they get here, should be a couple days, I'll show you on camera my new bugs. For x, or for the distribution, is typically denoted by an m, and if necessary, if you have multiple random variables, a subscript, and then it has an argument, which is usually an s or a t or a u, but it's whatever you want, and it is defined to be the expected value of e to the t times x. So that's like a g of x for an expectation for the law of the unconscious statistician. Next time, I'm going to tell you what moments are and why you would care to generate them. And honestly, I wouldn't care to generate them, but there's another use for this, which is in identifying distributions. So I could give you a distribution and give you a big function of it and say, find the distribution of this transformation. And it's just too hard to do the other way. But I'm going to try to convince you that moment generating functions uniquely determine the distribution. So if you find a moment generating function and if you match it up with one of the known ones in our table, then you can go back and read the name and you know the distribution. And this is going to be really key for big fat sums, x1 plus x2 up through xn. This is going to be how we're going to show the sum of n exponentials is a gamma. Next time on Mathematical Statistics.